All right. So both amplitude and wavelength. Oh, by the way, I don't think I mentioned, or maybe I did actually. But anyway, the SI units for wavelength would be meters, and yes, I did mention because I said that we don't always actually use meters. But being the SI, the official SI unit, means that whatever units we use for measuring wavelength will usually have to be converted to meters if we want to use them in an equation. So that's what it means to be the official SI unit. Both amplitude and wavelength are related to the amount of energy that's carried by a wave. It turns out that higher amplitude or shorter wavelength both correspond to greater energy. Okay, but the amplitude and wavelength can vary independently of each other. Okay, another way of characterizing waves that does not vary independently from wavelength is frequency. Frequency has a symbol that is the Greek letter nu. It is. It looks kind of like a V that's leaning to one side a bit, and in Greek, the letter nu is equivalent to our letter N, and I think they chose that because what frequency means is the number of waves that go past a given point in space per second. Okay, so it's the number of waves past a given point per second. The SI unit for frequency is the hertz, which has the symbol Hz. That is a metric unit. Oh, of course, being an SI unit, it's a metric unit. So you can actually use metric prefixes in front of the word hertz. So you could talk like millihertz or megahertz. And what a hertz really means is waves per second or cycles per second. Waves are often referred to as cycles, you know, up and down. It would be one cycle. And in practice, though, you don't actually, if you don't want to call it hertz, you can use one of these definitions, but you don't actually say the word waves or cycles. So you can also report hertz or, you know, frequencies as inverse seconds or seconds to the -1. So these would be the two sort of standard ways of doing it, hertz or seconds to the -1. Okay. Frequency would vary with speed normally. But the speed of electromagnetic radiation in air or a vacuum is constant. So in this case, the frequency will tell you a lot about the energy, and from that you can also find the wavelength. And so what it ends up is, because the speed of light is constant and all electromagnetic radiation travels at the speed of light, frequency in practice is proportional to 1 over the wavelength. So in other words, wavelength and frequency are inversely proportional to each other. So the greater the frequency, the shorter the wavelength. The longer the wavelength, the smaller the frequency. And both of these, frequency and wavelength, are related to the speed of light, because in fact, speed of light is equal to wavelength times frequency. This is nice, I mean, and it figures too, because if you figure, if you think about the units, wavelength would be in units, of meters in the SI system, and frequency would be in units of hertz, but in terms of the basic units that make it up, hertz would be considered seconds to the -1. Well, meters times seconds to the -1 would be meters per second. And that is indeed the unit for the speed of light, or any speed for that matter. We actually know what the speed of light is, at least in air or a vacuum. And actually it's known in other media too, like glass or water. You can actually look that up. And so we don't use the equation in that form very often. The way we use it is rearranged to solve for wavelength or frequency. So now if you know wavelength or frequency, you can find the other one in conjunction with the speed of light using one of these equations. Frequency would be speed of light divided by wavelength. And it's also equally true that wavelength is speed of light divided by frequency. And so those two rearranged versions of this equation are actually used quite often in the field of electromagnetic radiation, because it's quite often that you'll know the wavelength of something, like a given color of light. You'll know the wavelength, but you want to know the frequency. Or maybe vice versa. You know the frequency of a radio station, but because that's what the dial readout is. It's in, if you look at the dial on a radio, you'll notice that for AM it says KHZ or kilohertz, and for FM it says MHZ or megahertz. So if you're listening to a radio station with say a frequency of 91.3 megahertz, that means that 91.3 million waves go past a given point every second for the signal of that radio station. And using that number, 91.3 megahertz, well, you'd have to change the mega to a number, so it'd be 91.3 times 10 to the 6th hertz. You can actually use that number in this equation here to find the wavelength of that station. And in fact, as long as we're at it, why didn't we actually do that? Okay, so if the radio station has a frequency of 91.3 megahertz, what is its wavelength? Well, first of all, we'd have to change megahertz to the base unit, which is hertz, because that is the SI unit for frequency. And that would be 91.3 times 10 to the 6th hertz. That's not proper scientific notation. But this is not the final answer, so it doesn't actually have to be in proper scientific notation. You could actually use that number in the calculation if you wanted to, but I'm going to make it proper scientific notation just to be nice and neat about it. So that would be 9.13. Moving the decimal point made this part of the number smaller, so we have to make this part bigger. So that would be 9.13 times 10 to the 7th hertz. And now we know that wavelength is equal to speed of light over frequency. And that's 3 times 10 to the 8th meters per second over 9.13 times 10 to the 7th inverse seconds. So you have actually seconds to the -1 on top divided by seconds to the -1 on the bottom. So you'll notice those will cancel. And when we have 3 times 10 to the 8th, 3 times, okay, let's try that again. 3 times 10 to the 8th, there we go, divided by, and remember when you're dividing by a number in scientific notation, you need to use parentheses around it. So divided by parentheses, 9.13 times 10 to the 7th, those parentheses, equals 3.29 meters. That's actually the wavelength for that particular radio signal. That station with the frequency of 91.3 megahertz is a real station in the area. It's WBNY, the Buffalo State College radio station. You can listen to it anytime you want if you're in the vicinity. It's not one of the stronger stations in the area, but it reaches most of this area. And now we know what the wavelength is. There's 3.29 meters from the crest of one wave to the crest of the next for the signal that's going into your radio and resulting in conveying the signal of that station. Okay, so that's the kind of thing you can do with that. So let's see, also we were talking about frequency here. So for frequency, high frequency, or in other words, a large number for frequency, corresponds to high energy, and low frequency corresponds to low energy. With wavelength, it's just the opposite. Okay, so long wavelength corresponds to low energy, and short wavelength corresponds to high energy. And you can see how they would relate to each other because remember that all of these different forms of electromagnetic radiation are traveling forward at the same speed, the speed of light. So if the wave looks something like this, then that would be a long wavelength. And it would also be a low frequency because each wave is so long that you can't fit very many of them past a given point in space per second. And so that would be low energy. On the other hand, if the electromagnetic radiation looks like that, then that's obviously a very short wavelength. And a high frequency, because each wave is so small that you can fit a lot of them past any given point every second. And that's high energy. So radio signals tend to look more like this, while X-rays tend to look more like that. Even this is an exaggeration on both ends, though, because like I said, radio signals can be on the order of kilometers. The one for the radio station there is 3.29 meters. That's about 10 feet from the peak of one wave to the peak of the next. Whereas X-rays would probably be on the order of maybe 10 to the minus 12 or 10 to the minus 15 meters. And that would be very, very short, much shorter than this. You wouldn't even be able to see the individual waves if I'd drawn it to the scale. It would just look like a big, thick line. For visible light, which is a form of electromagnetic radiation, the wavelength or frequency will correspond to the color that we see. So the colors in the basically the colors of visible light are the colors of the rainbow. And you may remember that from high school or whatever: red, orange, yellow, green, blue, indigo, and violet. But very often we'll see light that looks white to us, and that's not one of the colors in the spectrum. So you might wonder, how is it that we can see white light, like light from a light bulb or the sun? And that's because when your brain sees more than one color at a time, your brain doesn't separate those colors. Your brain sort of averages all of those colors together and comes up with one overall average. When your brain sees all of the colors in the spectrum at the same time, it comes up with white. When you see a rainbow, it's because little droplets of water in the air are having the effect of refracting those individual colors and separating them from each other so that you can see them individually instead of all together all at once. And so that's really the only way that we can see the individual colors. So your brain averages out, when you see more than one color, your brain averages them out to one overall color. And so the colors in the visible spectrum, again, are red, orange, yellow, green, blue, indigo, which is kind of a deep blue, and violet. And those are the colors that make up the rainbow. When you see all of the shades of all of those colors at the same time, with no gaps between any of the colors and no shades of any colors that you're not seeing, then your brain comes up with a white light that seems very natural to us. And that's because that's basically the spectrum we get from the sun. Basically every shade of every color right across the visible spectrum. When your brain sees sort of representative examples of each of the colors in the visible spectrum, but there are certain shades of certain colors that you're not seeing, then what your brain comes up with is white, but it's a different kind of white. It seems kind of unnatural and unsettling in some ways. And that's because, well, it's not the white light that humans evolved to be accustomed to. An example of that would be like fluorescent lights. If you look at the individual colors given off by fluorescent lights, there are representative shades of each of these colors, but not every shade of every color. There are some gaps in the spectrum for a fluorescent light. And so a fluorescent light looks to us white, but it's an unnatural, sometimes even unsettling kind of white. Okay, of the visible spectrum, red light has the longest wavelength of all visible light, and also the lowest frequency, again, of visible light. The wavelength of red light is around 700 to 750 nanometers. And longest wavelength and lowest frequency means that red light is also has the lowest energy of any color of visible light. Violet light, on the other hand, has the shortest wavelength of any visible light, about 350 nanometers. And also the highest frequency, and the highest energy of any visible light. And determining what colors we see when we look at objects is really based on the absorption and reflection of individual colors. Okay, we see colors that are reflected, not absorbed. So we see the colors that are reflected. If a color is absorbed by an object, we don't see that because that particular color of light goes into the object, but it doesn't come back out again. In order for us to see it, it has to come back out and hit our eyes. So we see colors that are reflected from objects, you know, like solid objects. If it turns out that there's only one color reflected and the others are absorbed, then we see that color. That happens sometimes, that something looks like a certain color because it's absorbing all of the colors in the spectrum except that one color. It's possible that this pencil looks green because the paint on the pencil is absorbing every color in the visible spectrum except that particular shade of green. But it's much more likely the other way around. It's much more likely that there's one particular color being absorbed and we're seeing an average of all of the other colors. And for that, we can consult what's known as the artist's color wheel. And that is a wheel that's divided up into spaces, and each segment of the circle corresponds to one of the colors in the visible spectrum. Poor indigo gets left out. But anyway, red, orange, yellow, green, blue, and violet. This wheel is useful because the color you see is the color opposite the one absorbed. And the one absorbed is the color opposite the one you're seeing. So if the pencil looks green, that means that it's most likely that the paint on the pencil is absorbing red. And what we're seeing is an average of all of the other colors in the spectrum, and that happens to average out to green. If, say, the cap of the pen looks yellow, it's probably because violet is being absorbed. And so what we see is an average of all of the other colors, which averages out to yellow. The body of the pen is red, probably because green is being absorbed, and what we're seeing is an average of the other colors, which turns out to be red. And so on and so forth. So that's usually the way that color perception works. There are some versions of the artist's color wheel that are much more sophisticated than anything I can draw. Some of them actually have numbers around the edge for the wavelengths of each shade of each color. And so in that case, if you can narrow down what individual shade is being absorbed, then you can tell what individual shade that you'll see, or vice versa. But you get the basic idea here anyway. Okay, so to have a look at the electromagnetic spectrum overall, in which visible light is actually a very small fraction. It's funny because just about, well, so much, maybe not everything, but so much of what we know and what we perceive about the world around us is gained through vision, which depends on visible light. But yet visible light makes up a very small overall proportion of the electromagnetic spectrum. What I'm going over here is down at the bottom of page 281 in the book, and they draw it in a little more detail than I can, but you'll get the gist from this. So the lower energy end of the electromagnetic spectrum, which corresponds to low frequency and long wavelength, would be occupied by the lowest forms of electromagnetic radiation in terms of energy, would be radio or TV waves. And down here at the lower end, we're talking about wavelengths of about 10 to the 5th meters at the very bottom. So those would be the very longest wavelengths. That's actually 10 to the 5th meters would actually be 100 kilometers. Okay. And we're talking frequencies of about 10 to the 4th. 10 to the 4th would be 10,000. That sounds like a lot. But remember, these waves are moving at the speed of light, 3 times 10 to the 8th meters per second. And so if you can only fit 10,000 waves past a given point per second, those waves must be pretty big. So these are the lowest energy electromagnetic radiation. We are being literally bombarded with radio and TV waves constantly, all day, every day, unless you live, way out in the middle of nowhere, maybe. But in population centers, radio and TV stations broadcast their signals. And what broadcast means is they literally cast their signal out broadly everywhere, essentially. The radio and TV transmitters transmit that signal everywhere. And it basically covers everything in the vicinity. And if you have a radio with a crystal in it that's tuned in the right way, then it can amplify that signal and you can listen to the radio station. Otherwise, nothing happens. The radio and TV waves have such low energy that we can be bombarded by them all day and all night for our entire lives and never even know the difference. So it makes no difference. Next on the spectrum is microwaves. They are actually surprisingly low in energy too. They are used for a lot of radio type communications. I think some police band or emergency band radios fall into the microwave range. Cell phones are in the radio and TV range, but they're kind of right on the edge of microwaves. Microwaves you might think of as being pretty high energy because of microwave ovens, but microwave ovens are able to do what they do because, you know, even though the waves are of low energy, they have very high power. Power is the rate at which energy is delivered. And so microwave ovens basically deliver a small amount of energy, but they deliver it very, very quickly. So if you look at, you know, the power rating on a microwave oven is probably something like 1,500 watts. And that means that there's a lot of energy being delivered every second in the microwave. Next, we come to infrared radiation. Infrared radiation is still very low in energy. And it is getting to the point, though, where we notice infrared radiation as heat. So we feel infrared as heat. Next, we come to visible light, which I'm deliberately drawing as a very narrow band here because visible light makes up a very small proportion of the overall electromagnetic spectrum. But, you know, like I said, probably 80% of what we know about the world around us is based on vision, which is based on visible light. So it's kind of ironic that visible light makes up such a small proportion of the electromagnetic spectrum. Within the visible spectrum, we have the rainbow of colors: red, orange, yellow, green, blue, indigo, and violet. Red is the lowest energy color of visible light. Infrared is called infrared because infra is just a Latin preposition that means below or less than. And so infrared energy is less than red in terms of energy. Okay, so we go through the visible spectrum, we come to violet. That's the highest energy light. And the next step up would be ultraviolet or UV. Okay. Ultraviolet radiation, ultra is a Latin preposition that means greater than, or bigger than, or beyond. And so ultraviolet radiation is the next one beyond violet in terms of energy. From this point on, from ultraviolet on, we have what's known as ionizing energy or ionizing radiation. And it's called that because energy from here on up in the electromagnetic spectrum is capable of ionizing biological materials. By ionizing, of course, we mean basically removing or adding electrons to the biological material. Biological materials like, say, proteins or enzymes or DNA. And that's an important one because ionizing biological materials can do a lot of very bad things to your body, including cancer. And so from ultraviolet on up, you have to be very careful to limit your exposure to these types of radiation. Ultraviolet is, you know, it is ionizing radiation, but it is at the same time weak enough that it doesn't really penetrate the skin. So ultraviolet can cause damage, but it's usually limited to the surface of your body, like for instance, skin cancer or damage to your eyes, like cataracts, that kind of thing. But it doesn't really usually do much harm internally. With the next step, though, we come to X-rays. And of course, X-rays are famous for being able to penetrate through your body tissues. So X-rays can actually cause damage not only on the surface, but down inside your body as well. So they're even higher in energy than ultraviolet, and you really have to limit your exposure to X-rays. When you go to have an X-ray, they usually give you a lead-lined apron to put over all of the parts of your body that you don't want to X-ray, just to sort of limit your exposure as much as possible. The technician, of course, always ducks behind the lead-lined wall in the room, because the technician, as potentially harmful as X-rays are to the patients, they're much more potentially harmful to the technician, because the technician is in there using that machine all day, every day, year round. And so if they didn't duck behind the lead shield, they'd be in big trouble fairly soon, just because of all that exposure to X-rays. The dangers of electromagnetic radiation of high energy were not always appreciated, throughout history. When X-rays were first discovered, they were used for recreational purposes. People used to have X-rays just for fun. Shoe stores used to have, up until probably the 1950s, I think, shoe stores often from like the 1920s to the 1950s, shoe stores would have this device that basically judged how well shoes fit your feet, not by doing the obvious thing and asking you how they feel, but by taking an X-ray of your foot while wearing the shoe. And this was not just on photographic film, this was actually a live action kind of thing. So you could actually wiggle your toes and see the bones inside your toes wiggling around inside the shoes. And using that, you could see whether the shoes fit or not. This was especially popular among kids. They used to love having their feet X-rayed when they'd go to shop for shoes. It wasn't also harmful to the customers, because the customers only came in maybe once or twice a year for new shoes. But the effect it had was on the poor salesman. The machines were not shielded, and the poor salesmen were there having to X-ray feet for one person after another all day, every day. They're the ones who got the cancer. And these machines, were eventually scrapped, fortunately. And gamma rays are the highest energy electromagnetic radiation. So we've got high energy, high frequency, and short wavelength at this end. Gamma rays are produced by stars, like the sun. In fact, the star produces all of these types of electromagnetic radiation. Radio and TV waves, microwave, IR, of course, obviously visible light, and UV and X-rays and gamma rays. Fortunately, on Earth, we don't encounter gamma rays very often. Our combination of magnetic field and our atmosphere tend to filter out what gamma rays do make it here from the sun or other heavenly bodies. And that's a really good thing, because gamma rays are extremely dangerous. About the only source of gamma rays here on Earth would be nuclear radiation. Things like maybe uranium or plutonium give off gamma rays. They are extremely dangerous. Even a small dose of gamma rays can kill you. We're talking wavelengths on the order of 10 to the minus 15 meters. So that is really, really small. And frequencies on the order of 10 to the 24th hertz. Again, that's a huge number. That's more than a mole. That's basically 10 moles of hertz. And so that's a very, very large number. Okay, so that's kind of a quick overview of the electromagnetic spectrum. Oh, we're over time on this segment, so I'm going to have to end here. I'll be back in a moment.